Welcome, everybody. I'm so glad the SIIM conference gave us such an intimate setting for this meeting. I think social distancing is what they were thinking about when they gave us this room, right? Welcome back to in-person conferences as well. It's good to see you all in person. So the original topics for this talk were very focused on machine learning, AI in healthcare, AI and machine learning in imaging specifically. And then since we started preparing for this presentation to you, there's been a lot happening in the world that caused the topics to evolve a little bit. So we're going to be talking about AI, definitely, but we're also going to expand the discussion into the impact of AI in the world of cybersecurity. I'm sure some of you have seen the news recently. There's been two pretty big news. One of them, Apple announced that they're going passwordless, which sounds good, but what does it actually mean, right? I think that's a good question. And another this morning came up that there is a health system in Massachusetts that experienced a data breach of about 2 million patient records this last March. And they just found out about it, and they've been investigating, and they've been reacting to it. And that's exactly what I want to talk about today, the reactive nature of cybersecurity today and where we think it's going, right? So we're going to be talking about how do these AI companies develop their AI for healthcare and imaging. That's going to be the first topic, and then we're going to go into the impact of that into the cybersecurity side, because there's a tremendous amount of impact. So first, let's talk about what we learned as a company for the past few years. We like to introduce ourselves to our customers as the plumbers of the industry, right? We're sort of the quiet, in the background workers that keep everything running, right? We're not really visible to the clinicians or the technologists. Our work is always in the background. And in our capacity of plumbers, we run across a lot of information and a lot of lessons learned. These are some of them that we have for our partners in the AI world. Number one, very obvious but needs to be said, be clinically relevant. We get approached by a lot of AI companies that seem to have something really interesting, and they do, right? It's actually intellectually and academically very interesting and efficient, and then you present it to a clinician and they go, meh, I don't really see how this is going to be of any use to me. So that's number one, be clinically relevant and just do a little bit of homework before you start developing the AI and spending a lot of venture capital money doing so. Second, very important, know the clinician's perspective, meaning don't assume what the physicians do for a living, right? Their workflows, we don't live in their head every day, right? If you're a radiologist, you know what you do every day. But if somebody comes to you and says, well, this is what you do every day, and it's completely wrong, you've lost all credibility to this physician, and you're not going to sell AI to them because they don't trust you, right? Third, respect their workflow. So let's say you have a relevant piece of AI that you developed, a very effective algorithm, but you don't know where in that workflow your AI is supposed to fit. How are you going to deliver the value of your AI if you're causing the physician's workflow to shift in one direction or another? That's another lesson learned that's super important to us, right? Because our job as plumbers for AI and imaging is to make sure they fit in an existing workflow, that we're not causing the physicians to have to change their workflow in order to absorb this new AI. And by the way, this is times 20 or 30 if you've got all these physicians that are saying, we want these algorithms to be integrated. So as an IT department, can you imagine the complexity of introducing all of these algorithms into an existing workflow without interrupting or impacting a patient's data flow? Another super important aspect of what we do is advising AI companies to use industry standards. It may seem superfluous to mention it, but we've been even recently approached by AI companies that came out of some university system and have very impressive backgrounds in data science. And so their competence as data scientists is definitely there, but they don't even know how to spell Dicom, right? So that's a problem. If you're training your algorithms using JPEGs, you're missing all of the richness of the metadata available in the Dicom standard. So that's another super important rule we've learned. Another one that's actually a lot more elusive and doesn't really show itself until after you've already implemented it. Bias in machine learning, right? This is in the process of training an algorithm. How do you make sure that your data set has the plurality that it needs in order to avoid eventual bias and potentially misdiagnosis or false positives or false negatives in the findings? So to illustrate this point, I'd like to talk about an initiative that the Saudi Ministry of Health has just embarked upon. They have exabytes of imaging data available, and guess what? They want to do AI, but they're not going to be buying AI from Western companies. Why is that? Well, it's because their population needs to be served by algorithms that were trained on data that is relevant to their population. So there is, I wouldn't call it a mistrust, but there's an innate knowledge on the part of the Saudi Ministry of Health that if they buy all these algorithms, they're going to eventually have some issues, and it's not going to be as effective as if they fund AI companies to use Saudi data to train all these algorithms, right? So the problem of bias is very real. It's not visible at the surface. When you talk about AI, it's all shiny, new technology, exciting stuff. But there's a lot of discussion about how do you make sure those algorithms are not causing issues down the line. Next, have a viable long-term business model. Let's say you successfully develop a piece of AI. The algorithm is phenomenal. It's 99% effective in detecting something in an image. You've got funding. You've got venture capital funding. You've got runway for 24 months. And then there's a crash, and there's no more funding available. And your company literally needs to let go of people because payroll is gone. Well, now you have a hospital or several hospitals, maybe the proof of concept hospitals, that adopted this technology, are happy with it. Now they're faced with a discussion of, okay, do we want to buy the IP and own this IP because we have a right to it contractually, right? Because the IP was put into an escrow account. But the hospitals don't want to be in that business. So it's very important that you know when you have a successful algorithm that is being deployed and sold in a way that's replicable, right? So that if you run out of money, that the hospitals are not left with an algorithm that's not supported anymore. Next, another cardinal sin in imaging workflows is impacting the workflow because of latency issues. So this is, again, a function of where in that workflow are you inserting an algorithm? Is it at the scanner level? Is it built into the scanner, in which case the images already come with an AI finding? Or are you post-processing this? Are we receiving the images, sending them to an algorithm, waiting for a result, and then presenting it to the radiologist? Well, that could be a problem, right? If the resource, especially if it's a cloud-based imaging algorithm that is presenting with some latency issues, or the servers are unavailable, now you have a radiologist waiting for their images because the results weren't available yet from the algorithm. So introducing latency in a clinical workflow is a big no-no, and that's why it's so important to understand, right? Number 3, respect the clinician's workflow. Well, it's not just in what sequence of events the radiologist works, it's make sure you don't slow them down, right? There's not enough radiologists in the world in the first place, so if you cause them to work slower, you're not going to have credibility. Another one seems to be obvious, but be more accurate than a human. Literally, this goes to the validity, be clinically relevant, but if your success rate is barely above or equal to what a human radiologist would do to detect something in an image, chances are that we're not going to want to invest any time in that technology. It should be above, and hopefully well above, the accuracy levels of a human. Next, generate usable results. Why is that important? Well, algorithms have different sorts of outputs. It could be an overlay, right? It could be a Dicom SR, a structured report. It could be an HL7 result. It could be a fire call, right? All of these things have different manifestations that need to be sent to different places, right? So if you send a Dicom SR, maybe that needs to go straight to Nuance to pre-populate a report, the findings. Maybe it needs to be enriching the data set and sent with the images as an overlay, as a Dicom object. So when you're designing an AI algorithm, you need to be thinking about how am I delivering the value that my algorithm proposes to provide. So we've seen it way too often where the result comes out and it's non-standard, so now we have to massage the data, translate it into something else, and then send it to the appropriate place. Last but not least, many of these algorithms are developed in a cloud. Maybe they're using GCP or AWS or Oracle Cloud or Azure, right? Those are the big four now. Well, naturally, because you've been developed in those infrastructures, you're going to tend to want to make those algorithms available as a cloud-based solution. Well, guess what? That takes Kaiser Permanente out of the running. You're not going to be able to sell your algorithm to them because they don't do cloud. It's a policy, right? Or at least not to the extent that you would like them to. So be equally deployable in on-prem environments to deliver your value and in the cloud. So these 10 rules, if you check those boxes, even as a hospital looking at the technology, if an algorithm checks those boxes, then you have a pretty good chance that it's going to be a successful and long-term implementation. So this, again, seems obvious, but unless you're talking to a data scientist that happens to also be an informatician in the imaging world, it's going to be tough for them to learn these new standards for themselves. So you want to make sure that when you're building an algorithm, conform to Dicom, know what HL7 is, and preferably, to be even more interoperable, use a RESTful API, Dicom Web and or Fire or both to deliver your value to the workflow. So this may not be new to a lot of you guys because you're at the SIIM conference and you're pretty educated about this, but these are things that we, as plumbers for the industry, had to learn pretty quickly. We learned quickly that it takes, on average, about 100,000 similar images for an algorithm to run through its neural network and recognize something consistently. That's learning one thing, 100,000 images. So you can imagine that you need a lot of images de-identified, prepared, cleaned up for consumption by an algorithm so the machine learning process can take place. So you've got inputs, and then you've got these arguments that the algorithm needs to learn in order to create a consistent output. And so what do? We do a variety of things to teach an algorithm something new. There's 3 methods. This is the first method. Unsupervised machine learning basically says, here's a bunch of images, categorize them. But you're not giving it any more input, right? The algorithm needs to decide on its own, based on the sheer magnitude of the data set coming in, whether to recognize that all of these images are images of a golden doodle or fried chicken. Chances are, without further input, the algorithm is not going to learn something good. Yes, that makes me hungry too. Supervised machine learning is what happens most successfully in what we do in imaging, right? You need somebody to actually tell the algorithm what it's looking at. It's labeling. That in and of itself is a challenge for our industry because there's not that many radiologists to start with, and not many of them are willing to moonlight to do labeling for machine learning, right? So this has been an arduous process for years. There's various companies that have come up with different models. Some of them have incentivized radiologists with equity in the company in order to invest them into the process and get some of their time to label these images. But supervised machine learning essentially says what you're looking at here is a nose, right? But if the algorithm was looking at this image, it could say, well, this image contains a nose too, right? But no, you're only labeling the ones that do contain a nose. So over time, this algorithm is getting more and more intelligent at recognizing this. There's another method that is more of a gaming approach, and this requires some input along the way, right? So you're not just letting the algorithm go wild with the learning. You're basically saying, yes, you're right, this is a piece of fried chicken, or no, you're wrong. And so the algorithm, by getting more or less points, learns what is correct. There's a lot of other interesting things that have happened in this world, like Stanford University a few years ago created something called a radiology swarm, where the algorithm learns from collaborating radiologists from around the world to recognize pneumonia in an X-ray, right? So depending on the percentage of those radiologists saying this is pneumonia, then the algorithm is learning from all of these radiologists around the world that the most amount of them in that quadrant of the choice is mostly correct, and this is pneumonia. So there's a lot of different methodologies to teach an algorithm something, but these are the most prevalent ones. So let's talk about the magnitude of the data that goes into machine learning. Our first project with Hospital for Special Surgery in New York was an orthopedic algorithm that we helped them develop. Now, we didn't develop the algorithm, but we prepared almost 6 million exams that were fed into the algorithms. There were several of them. So the challenge was multiple sides of the challenge. Number one, the data exists in an archive. And guess what? That archive is clinical. So if you do a massive query for 5 million exams, even if you do over a period of several months, you're going to cause some problems at the PACS level. The PACS is not going to be able to do it. And so the first challenge was to gain file-level access to the images versus query retrieve, right? So if you do Dicom query retrieve on 5 million exams, forget it. It's not going to happen. So we gained access because we're partnered with the PACS company, and we had a close relationship, and so we were able to scan the volumes, the storage, and get all those images in. And the first step was for us to de-identify the images according to a really strict set of rules. And I'm not talking about the ACR, 18 fields that you need to pay attention to. That cookie cutter approach does not work in what we do. We tried it, it doesn't work. We can go into why it didn't work if you'd like, but it's the bottom line, it didn't. The second step is to QA what we did in the first step, right? Because it's possible that the rules you created to de-identify an image did not catch everything. This happened when it came to secondary captures. So scanned images from a VIDAR scanner are problematic in this process, and you want to get them out of the process because they have PHI in completely unpredictable places in the images. That's a problem, right? So we learned that and created this secondary QA process to ensure that the first one did its job correctly. And then you deliver the images. Typically, those images are going to be delivered to a cloud-based repository, a data lake, that then presents the AI companies with all of the data that they would need to create the cohorts. Say, give me 100,000 MRI of shoulder MRIs to do this algorithm. But at this point, we're disengaged from the process because we've done our job, right? We've de-identified the images. Now it's up to the AI company to develop its algorithm. And ultimately, the process takes them through all of their cogitations and deep learning. The algorithm is born, and they hopefully get FDA clearance. That is the process that was behind all of the lessons learned for our company. So on-prem versus cloud-based, the distinction from a workflow perspective is not that different. On the top side, you see it's cloud-based. On the bottom, it's on-prem. So we talked about that in a previous slide, right? Either you are able to deploy your AI both on-prem or in the cloud, or you're not, right? If you're strictly available in the cloud, then the process of providing your value to a hospital or radiology group is going to have to take them to the cloud, which means you need to at least encrypt or de-identify some of the data, right? Because the hospital's infosec policies would not let you, unless you're on a VPN and you have a BAA and all of that stuff in place, then you would be, you're going to have to de-identify the images on the way, which means you're creating more latency in the process. But it can be a very elegant process, right? So you get the images from the scanner. We can look at all of the metadata in the Dicom headers, and based on the nature of the exam that's currently passing through, we can say, oh, in this Docker, there's an algorithm that should be looking at these images and getting us a result. So what do? We leverage Dicom Web completely to share the data with the algorithm and receive a result back. So the Dicom Web standard contains three things, right? Keto-RS, Wado-RS, and Sto-RS. So metadata goes through Keto, pixel data goes through Wado, and then on the way back, we get a result through Sto-RS. That is the most elegant way to do this. Now, can we do this kind of workflow with all of the algorithms out there? No, because not all of them are Dicom Web compliant. We would have to go DMZ instead of RESTful API, which is less efficient, right? The integration takes a lot longer. But then we also have an opportunity to intervene at the result level because, as we mentioned earlier, these algorithms have different outputs. One of them might give you an HL7 message. Another one could be that Dicom overlay that needs to go on the images. So depending on the nature of the result, we're able to push it either to the PACS, to the dictation system, if it's Dicom SR with values that need to pre-populate a report, or an HL7 message straight to the EHR, as an example. So now we get into the problems that all this AI has created for us. All of you have been, I'm sure some of you have been to RSNA, right? Anybody not been to RSNA in this room? You're very lucky. So AI is just this tsunami of things coming at us in the industry, right? Every university in the world, there's no country in the world that has exclusivity of AI supremacy, right? There's great AI coming out of all these countries, all these universities, all these students. And so the problem is it's impacting our industry in a lot of different ways. And this is where we're going to get into the cybersecurity aspect of AI, versus how does it work. This is part of the problem that it's created for us. Radiologists are creatures of habit. They work hard, they read all day for sometimes 12 hours in a row, and their user experience is very important to them. But some of them work from home. Some of them, part of the time, will work from an office. Some of them will read at a hospital to provide their services. A radiologist is not a static position anymore, especially with COVID, with a lot of people that migrated to their home office. Now, the cybersecurity side is making it harder for them to access their data. So the subject of this talk is the balancing act between making it easier for the end users to access their data while still keeping the infrastructure safe. right? So how do we do that? How do we improve on that? These are the things that are currently done across the board to authenticate individuals, people, which, by the way, is now soon going to need to include machines, the Internet of Things, right? It's not just people logging into a system to consume data. It's also the algorithms that are assisting them that need to be a part of their footprint. So you either use something you know, like a password or a PIN, or something you have, like if you're in the military, the CAC cards, I'm sure you've seen those, and something you are, meaning your fingerprint, your iris scan, maybe your voice print. We use a combination of all those things these days, right? It's become such an ingrained part of our lives that we don't really realize it anymore. But any part of this doesn't work, and our workflow is interrupted. And that happens a lot. You have a lot of irate customers, a lot of IT people that need to deal with irate physicians because they can't log into their system for whatever reason. These are some of the authentication protocols that are commonly used. There's a lot of different solutions for single sign-on. Single sign-on has been around since 1991, right? That was kind of the precursor to all of this multi-factor authentication world. The problem with single sign-on is that you have a single key giving you access to all of these systems all at once. So if that first pass-fail test is failed, then you're not accessing any of these systems after you try to sign on. Here's the fundamental problem with not just malware, hackers, data hostage situation with cryptocurrency, all of those things are systematically going after these passwords, and they're getting through. They're actually getting them. How did Shields Health get attacked in March? Brute force attacks, phishing, you name it. There is a way that these companies are getting through, these hackers, whether it's from North Korea or Russia, it doesn't matter. It could be a bad actor here in the US. It could be a disgruntled former employee that happens to be a hacker that is now leveraging these vulnerabilities. But make no mistake about it, they're systematic and relentless. If there is a vulnerability to find, they will find it and they will exploit it. It's Murphy's Law. Anything that can go wrong will go wrong. And so here's the issue. We've been reactive since the early 80s, with virus attacks, patching. It's always the lesson learned that tells us, oh, that's what we did wrong. Let's go back to the drawing board. Let's write this patch. Let's distribute this patch to all the end users and hope that they actually do it, right? Apply the patch. So security or infosec is largely this reactive exercise that looks to the past, looks to logs, to paint a picture of what happened in order to prevent from that thing to happen again, right? But what about all the new things that are going to happen? There's no proactive thinking involved in this. And so what we need to be thinking about, the future of authentication in healthcare needs to go beyond this binary pass-fail thing. Because if you pass and you're a bad actor, you have unfettered access to everything behind that first door. There's nothing else to keep you from opening all the doors inside. We have an IoT problem exacerbating this problem of accessibility. Why is that a problem? Well, it used to be with 4G LTE that you would have up to 4,000 devices per square kilometers that could access a cell tower. Well, now 5G is making it possible for up to 1 million devices, all of which could be a target for hackers, right? So you're actually increasing the number of targets that these hackers can leverage in order to access a network. In your home, your temperature control, well, cloud-based information, right? There could be access your personal data. Same thing if you have a Tesla, all of the software updates, all of the, there's a lot of different ways to access data through the cloud as well. And so if you're offering with 5G, not just the human targets, but all of the devices that assist these humans to do their jobs, now you're actually creating a bigger problem. Incidentally, I wanted to go over this with you because very few people understand what 5G actually means, but 5G is only helpful to a point. It's only helping you from your cell phone here to the closest cell tower. Because from that cell tower, between your Google query here and the Google servers here, yeah, you're going down to under 5 milliseconds of latency between here and the cell tower, but you're still having to deal with the normal network infrastructure to get your query to the Google server and back, right? So you're really, it's a very, I don't know why we're celebrating 5G so much, because it's actually a fairly small incremental success as far as I'm concerned. So, anybody ever see that movie, Quo Vadis? Cecil B. DeMille movie from the 70s, I think? That movie stuck with me since I was a kid, because I absolutely love Roman history. But this is an illustration of the pass-fail test when you're trying to log into a system. There's one sentinel, one password, one MFA, or multi-factor authentication methodology being used. Once you're behind, once you get past this first sentinel, who else is watching? Nobody, right? You're in. If you're a legitimate data user, you should be free to access your data, absolutely. But what if it's that disgruntled employee that is now hacking into the system for nefarious reasons? Here is where we see the future of authentication going with leveraging of AI and leveraging of data science. And this is very exciting to us because as a company, right, as the plumbers, we often are right in the middle of a workflow that could have caused a breach somehow. And even though our server is very safe and we've never been the cause of a breach, we're still in those workflows. And so it's interesting to see where the future of authentication is going. Imagine you get past that first sentinel. Well, there's another sentinel behind that door. And there's one down the corridor. And there's another one in front of the next door, right? All of these sentinels are actually leveraging data science to provide a safer user experience and a smoother one. So there's a lot to unpack here. Continuous, passwordless, frictionless authentication. All of these words have a different impact on this proposition. This is what's happening. All of these applications that we all use, whether they're consumer applications on our iPhone or even a Google device, Android device, all of these applications that we use on our desktops, cloud, SaaS, doesn't matter where, they produce massive amounts of log data. The log data are typically only used to retrace something that happened, right? Paint a picture of maybe a mishap or a data hack that happened. The idea is to take these logs and aggregate them into data lakes and create a behavioral model of a legitimate user, a known legitimate user, right? The footprint, what are the apps they use, from what IP address? Are they geographically accessing the data from a different country today? Are there two people trying to use the same credentials at the same time, right? All of those things are an online behavior footprint that can be documented and leveraged to create a digital persona. That digital persona doesn't need to be a human only, right? It could also be a scanner, right? What if it's, I don't know, what if you're leveraging these new ultrasound devices from Butterfly Networks? What if you're using the new MRIs that Dr. Siddiqui has been putting on the market? You know, mobile MRI is a phenomenal concept, but it's now a moving target, right? What if it's logging in from a different IP address? Are there other ways to verify that this scanner is a legitimate user of the network? So this is how this concept would work. we have what we call producer applications, right? All of these things that we use as end users, apps on our phone, Salesforce in a SaaS application. So we need to be really good at keeping track of these logs that are in mobile, workstation, cloud, on-prem, or SaaS applications across the board. Like, for example, Microsoft does a very good job of analytics and anti-malware with E3 and now E5. They're getting better and better, but they're not across the board, right? They're over here and they're over here, but not necessarily on mobile devices, right? So you have a hole in that strategy if you're relying strictly on Microsoft to provide cybersecurity. So the idea is to aggregate all these logs that are coming out of all these applications in all these realms and aggregate them into a broker. Now, this technology some of you may recognize as Kafka Topics. Any of you have heard of Kafka Topics? It doesn't need to be just a single vendor. It happens to have been invented by Apache, but Kafka Topics are essentially log aggregators, right? All the producers of the logs are contributing them and making these logs streaming data that can be analyzed in real time by algorithms. So instead of having a static, okay, let's look at this log and try to correlate data to retrace a mishap, now you have continuous monitoring by AI that are looking at a certain behavior and using the benchmark of your known persona to see if you're doing something that is nefarious or not. And so there's also real-time threat intel being produced by all of those cybersecurity companies, right? There's global intel being shared about new possible threats. And so if you, in real time, let AI, which is far better than humans at looking at massive amounts of data, if you let them do their job and actually monitor and learn continuously from your behavior while you're working, right, in your everyday duties, now they can assign a real-time risk score to the current behavior. And based on that risk score, either low or high, it's going to either maintain your access, your authentication, or it may restrict it to certain parts of it, or it may deny you access altogether and cause you to re-authenticate. Guess what? Maybe with a password, right? So we're saying passwordless, but that is a misnomer. Passwords, I feel, we're not saying are going to go away altogether. I think where we're going with continuous authentication is that we're going to be leveraging these multiple methodologies together, especially leveraging of AI to continuously monitor and compare behavior with a behavior model. The data science behind the models are coming from us, from our everyday behavior. And guess what? We're already doing this in finance and banking, right? You routinely get a message saying there's a suspicious charge that happened on your credit card. It's not a human looking at every transaction you do, right? It's one of those continuous algorithms that are looking at how much money do you typically spend on that credit card, right? If your average is $300 per transaction and all of a sudden there's $3,000, well, that's not part of your normal behavior, and it's going to ask you to re-authenticate and confirm it is you. Same thing with authentication of all of our applications in the healthcare environment. Same concept. So there's been something that we've become more and more aware of. Some of our customers are implementing what they call zero trust. We've run into some issues. I'm actually very eager to hear from this audience what your experience with zero trust has been, because ours has been dismal for some pretty simple reasons. We got some support calls from some very high volume customers saying their images aren't getting through anymore. And so we start looking, right, through the logs, manually, human looking at logs. And we realized that because of the zero trust implementation, every Dicom association was being checked. So if you're sending a 3,000 slice CT, guess what? You're going to put some latency in a workflow. Not good. So another problem is that the token server that you're trying to authenticate against, that server can go down like any other server, right? So if it's down, what do? Your workflow is interrupted. It's also an attractive target for people that wish you ill, right? So we don't trust zero trust. We have zero trust in it. So, like I said, I would love to hear more about that because I've heard of some successful implementations of it in radiology, and I want to know what those distinctions are. So at the end of the day, our job as technology companies is to make our end users' life easier while they serve patients, right? Ultimately, it's all about the patients and our ability to serve their needs in real time. And so you can see in this chart that using what we call a bio-behavioral model that leverages real behavioral data, logs, your digital footprint, your digital persona, in order to authenticate you and continuously authenticate you, provides for a better, smoother, frictionless experience for the end users. So you're instead of having this tug of war between infosec and the user experience suffering from that, you're actually giving them the best of both worlds. You're satisfying infosec by giving them massive amounts of control over the traffic, and you're giving the end users massive amounts of control over their user experience. So that's why we think this is the most natural way that authentication is going to happen in the healthcare world. Not just healthcare, any industry really, because cybersecurity could be breaching utility companies, hospitals, radiology groups, governments, all of those could be leveraging this kind of technology. Which brings us to almost a philosophical question. By going passwordless, we're essentially saying, step onto this airplane, there's no pilot, it's all AI driven. Are you going to get off the plane because you don't trust it? It's almost the same thing, right? If I say, you're logged in, you're passwordless, you're going to say, what do you mean? Is this safe? Is this something that I can trust? Because there's no password. I'm so used to entering a password that if you give me an environment where I don't have to enter a password, my natural instinct is going to be to mistrust it, right? Are you sure this is secure? And unfortunately, we have some real-world experience with this. You remember Sully and the landing of that plane on the Hudson River? They ran countless simulations with AI flying the plane, having that same mishap. None of the simulations landed the plane on the Hudson. It took a human with human intuition to compute that it was safer for that plane to land on water and float to get all the passengers off, but none of the AI simulations got it right. So in one way, we're saying, yeah, AI is this great way to do all these great things, but to what extent are we going to trust them with our everyday lives, right? So I can't wait to be on a plane that has an AI pilot, because I know that under the best of circumstances, that AI has a better flight safety record than any human. But at the same time, I'm going to be thinking about Sully, right? So that constitutes my presentation to you. We're going to open it up to questions. And how are we doing on time? Yeah, we have exactly 17 minutes for Q&A. And like I said, I want some input about zero trust. I need to learn more about it because I don't feel like I'm fully educated on that topic yet. These are some of the resources that were used in some of the content that we presented today. The continuous authentication technology, if you want to learn more about it, there's a company called SecureAuth that just acquired Accepto Corporation in Portland. They are the data scientists behind this new thinking and technology, and that technology is actually in use already. CVS Corporation is using it. There's several large corporations using it. So thank you for your attention. I appreciate you being here. Great to see everybody in person. So let's open it up to questions. Yes, you want to step up to the mic?
Well, firstly, I just want to say I thought it was a fantastic presentation. And
Thank
you
you.
had some really, really dense, value-dense slides. The one slide with the 10 criteria for success, let's say, for AI was really interesting. And I thought there was an implicit point that I have found pretty interesting. I guess my background is similar to yours in that we would also consider ourselves as plumbers in this world. And one of the things that I think underlies a lot of the points that you made was that folks developing algorithms need to ask themselves the question of what they consider to be within their wheelhouse, in the sense that a lot of the criteria that you listed is not algorithm development per se, it's all that plumbing stuff. Mm-hmm. And do you actually want to have that plumbing in-house, or do you want to find and select the best solution that's either off the shelf or open source or what have you, and utilize that one? Because something that we've seen a lot of is highly duplicative, very expensive and messy approaches to build that functionality in-house. And it's everyone doing the same kind of plumbing exercises and running into the same issues and spending a lot of money on validation and certification and so on. And it just adds a lot of time and expense to a process that you might or might not want to actually have in-house. So I just thought that was an interesting underlying kind of piece of that there. I also thought you made a really interesting point about the similarities in workflow between on-prem and cloud for an AI workflow. But I thought it might be kind of interesting to talk about the different options you have to deploy capabilities at the edge. So one of the things that we found really interesting is you talked about secondary captures as an example, right? Something you might seek to detect and not scoop up as you're doing your automated analysis. Doing that kind of data cleanup at the edge is awesome, because you're not sending all that stuff up to a central processing engine and wasting bandwidth and so on and adding latency. So that's kind of interesting. I wonder as well, too, you'd mentioned de-identification, and generally speaking, that needs to happen at the edge, ideally. How do you guys go about configuring your de-identification workflow per whatever the customer need is? Because you've mentioned moving away from the 18 tags kind of standard approach, and absolutely, but I'd just be curious, what does that look like?
Thank you for your questions and comments. So de-identification for most hospitals, because of the sensitivity of PHI, in our experience, right, it could be shifting away from our experience. But the hospitals don't want the data at the edge, to be de-identified at the edge. They want it to be fully safe, ready to go, long before they reach the edge, right? So that's why we set up a primary de-identification engine, as well as a QA step as an insurance policy to make sure that our primary engine did its job correctly, because we're not flawless either, right? So it's a process of iteration, and you test it until you feel, that's right, we have a cohort with no PHI in it, right? So the 18 suggested ACR fields to pay attention to are perfectly valid. Here's the problem with the cookie cutter approach. A lot of companies take major liberties with the Dicom standard. Different vendors put different types of data in different fields. Some fields may be custom fields that don't exist yet, right? But they're convenient to the vendor. And if we don't know the entire data set, right? If we assume that we're safe because we looked at those 18 fields, and so we move forward, there might have been 3 custom fields that are buried in the data set that you didn't pay attention to, that contain data that could be traced back to a patient. And so our process is a lot more labor intensive, but a lot safer, in that before we even begin to go to production with a de-identification project, we need to know every field. We need to go through the data set. What modality type is it? What scanner did it come from? Because you could have 2 CT scanners, and the second one was a second generation or third generation scanner that has a different Dicom file set coming out. So what we found with de-identification is that you can't make any assumptions that you're safe. You really have to, lift every stone, look under it, which is definitely labor intensive, and we don't do it by ourselves. We do it in collaboration with our customers. What's also important to recognize is that every AI algorithm or every clinical trial that the de-identified data is for has a slightly different purpose, right? If all the algorithms were doing the same thing, then just one de-identification method would do the job. But what if the de-identification needs to be different, right? Either you want all the fields to be permanently de-identified, so you can't trace anything back, but what if you do want to trace back to a patient? What if it's a clinical trial? Now you could use a combination of permanent de-identification and selective encryption of certain fields. Well, you can't do that automatically. You have to actually design it to do that way. So that's been our experience, right? We don't in any way invalidate what the ACR is suggesting, right? The 18 fields that they're suggesting. We're saying you have to go way beyond that if you're going to be systematically right about your process. Does that answer your question?
Yes. Yeah, I just want to get a sense. Another kind of interesting point that I think you touched on is, we do a lot of stuff with data de-identification, and for this kind of an audience, I think the larger issue tends to be not necessarily the data that's de-identified, but actually how overzealous is your redaction approach, and what are you throwing away that the downstream consumer on the algorithm development side might need for that data to be valid. And so we get a lot of people saying, we actually get a lot of resubmissions that are required because the data was far too overzealously cleaned. And so we're missing all the quantitative fields that we require to train our algorithm. So they're just interesting.
Yeah, and if that happens, during the discovery process, that needs to be pointed out in the statement of work. Because chances are you're going to catch that before you go to production if you do your job right. And so you should be able to catch that. We ran into that issue countless times in the process of preparing data because you have metadata and you have pixel data. Well, you can mask or blur certain pixel coordinates in an image, but you can't be systematic about it, right? You have to make sure that it's only PHI that you're blurring out and not clinically relevant annotations or something, right? So again, you can't just cookie cutter this thing. You have to really take a very empirical approach to, especially to the large scale projects. If it's a small cohort, for an experimental reason, you can take more liberties. But in our job, when we're expected to deliver clean data in the millions of images, we can't take those liberties. We have to be thorough before we go to production. Any other questions? Yes?
Do you have any experience with de-identifying like the facial structures? We're getting more and more pressure to, when we're sending images, that anything of the face needs to be de-identified in some way.
Right. So
we don't have that software. We don't have a way to do it.
So you're talking about reconstructed images, not visible light pictures of a patient, right? You're talking about CT slices, CT of the head, that could be formed into a recognizable individual. So we don't have that software, but we can apply that software. There's several companies that specialize in that where, a 3D reconstruction will include a blurring of the face once the reconstruction is complete. Again, we're the plumbers, not the clinicians, right? So our job oftentimes will be limited to what we can do in a highly automated fashion. And so we need specialized companies like, we have our colleagues from SoftNeta here who specialize in viewer technology. They have 3D technology, they have MPR, they have a lot of the stuff that we don't have because we're not a viewer company, but we're complementary. So to address that, you would need to bring in another piece of software that we can integrate via Dicom Web, very clean RESTful API integration. Yep.
presentation. When you talk about zero trust, you give an example of like a city study with 3,000 objects, and you mentioned that you check every object. Do you actually check, so you're not just checking at the association or connection time? You actually check every object?
It's every association.
Okay.
So you could have multiple objects in an association, but if you have any kind of interruption in that association, now you're going to need to re-authenticate again.
Right. Oh, okay. Okay. So once the association or the Dicom web connection is trusted, then all the objects that are coming through is going through without additional.
Theoretically, yes.
Right. Okay. All right. Thank you.
Correct. Anyone else? Maybe there's a carbon monoxide leak in the room, I don't know. No other questions? We're good? I'm happy to answer. David, do you have any questions?
No, I was going to talk to you after.
Okay, very good. Well, I'm available to any of you, via email. You can reach us through our social media as well. This is a topic that I'm very passionate about, especially the cybersecurity piece. Because we're facing way too many of these threats increasingly, and we have to start being proactive versus reactive to these bad actors. Thank you very much, everybody.